Sure.
Awesome. Hey, what's up? Cool.
Hey.
All right, James, do you want to just kick things off?
Yeah, I'll share my screen, like talking about the series, and then introduce Lindsey, and then we can get started with the presentation. So, let's see. Yeah, so welcome to Multimodal Weekly. This is a webinar series hosted by our team here at 12 Labs, and essentially we meet every Friday at 1:30 p.m. Pacific time. Here's some of the topic that we tend to cover on a weekly basis. News research topic in multimodal AI, applications of this technology in different verticals, open source or closed source technologies, projects to video model that the community members plan to share, infrastructure changes technologies, and sometimes we also have a team member from 12 Labs discuss some tutorials and guides on using our technologies. In previous session, we have a wide ranging of speakers talking about scaling multimodal in production, with vector database, to usage of multimodal AI in healthcare, to working with different type of multimodal format, to even like working on diffusion models, etc. So our speaker today is Lindsey Lee, currently a senior researcher in the computer vision group in Microsoft Cloud and AI. Quick introduction about her. Before joining Microsoft, she obtained a master's degree in computer science from Purdue University in 2018, and her current research interests include vision and language pre-training, self-supervised learning, and adversarial training. So today, she will give a talk about multimodal understanding with large language model. So I got a chance to watch her CVPR presentation on multimodal agents. It was like super, I guess, excited to invite her to our series, because a lot of the work that we're doing at 12 Labs involve vision language and video language modeling that was inspired a lot by some of her previous work in the value challenge, Hero, ClipBERT, Initer, just name a few. And I'm sure that Lindsey can talk more and share her thoughts on the evolution of the field, given her experience doing research in the past 4 or 5 years or so. So with that, just quick logistic note. Feel free to send your question on the chat. As our speakers can talk, and we'll also have a Q&A session when she's finished. So with that, I'll let you share your screen and we get started with your presentation.
Yeah, thank you, James. So let me try share my screen. Anything happen yet? Cool.
Yeah.
No?
It's
Yeah?
working.
Okay.
It's working great.
Yeah. So as mentioned by James already, we're going to cover multimodal understanding with large language models in this talk. And since James already introduced me, so I would just skip the introduction part. And also some apologies if you have seen my talk on multimodal agent, it's going to be very similar. So yeah, don't expect too many new things in this talk. Let me get started. So in today's talk, we're going to cover 2 subtopics under the big title, Multimodal Understanding with Large Language Models. Both are based on the recent advances in large language model for language understanding and generation. And we will cover 2 ways to build a general purpose multimodal interface. One is to train a multimodal large language model, and the other is to train multimodal experts with large language model. And I also noticed like the author of Lava has already talked before, so you will also see similar content here. Yeah, I apologize for that. And yeah, this is the first part, building large multimodal models with large language models. So first, a little background on large multimodal models, just to lay the basics on the model architecture and training objectives. So large multimodal models in their current form is largely a image to text generative model, which takes image as input and the output is a text sequence. All of the model variants share very similar model architectures, where they have a vision encoder and a connecting model between the vision encoder and the language model. I noticed like I'm very dark. Yeah, maybe something wrong with my camera. But hope you guys can focus on the presentation slides more. Yeah, let me continue. So yeah, it usually consists of a image encoder to extract the visual features and a language model to decode the text sequence, and the vision and the language modality can be optionally connected by a trainable connection module. That's the model architecture. And on training objectives, it typically employs autoregressive loss on the output text token. So for the attention mapping, the transformers, if you are familiar with that kind of architecture, image tokens can attend to each other, and the text tokens will just depend on all the image tokens and also the previous text tokens. So it's more like a causal mask for text generation. And let's take a look at some examples that implement this large multimodal architectures. So for the large multimodal trained with image text pair data, take GIT and BELIEVE2 as two prominent examples. They have achieved SOTA performance on many traditional VL datasets. And GIT initialized the image encoder with a contrastive pre-trained Florence model and train a language model from scratch. On the other hand, BELIEVE2 frees the weights of a pre-trained image and language model and train a lightweight Q-former, which is the connecting module in the previous slide, and it shows higher sample efficiency with the bootstrapping training method. So these are all before the multimodal GPT-4 came out. So quite strong model with just single image text pairs. And for models trained on interleave image text data, this Flamingo is one of the first example in this area. It connects the frozen pre-trained image and the language models by adding novel architecture components in between, specifically a perceiver sampler module that helps to reduce compute complexity, and a gated transformer module helps stabilize training in the initial stage. And Flamingo is trained on a mixture of complementary large-scale multimodal data from the web, including both image and video, and in the format of the interleaved multimodal instance. And they don't take any data annotated for the machine learning purposes. After this training is done, Flamingo can be directly applied to vision tasks via just simple few shot learning without any additional task-specific tuning. So you can just give demonstrations, for example, the dog image, and this is a very cute dog, and give the testing sample of the cat image, and it will output a similar sentence like this is a cute cat or something like that. Yeah. Okay, now let's take a step back and review the foundation of the two questions we are trying to answer today, and take the big large language models from OpenAI as examples. So here we highlight some of the most appealing properties for each model. From GPT-3 to GPT-4, we see two new properties, instruction following, and multimodal inputs. So this reveals the gap to actually achieve GPT from what we have seen before, like the GIT, Believe, and the Flamingo. How can we perform instruction following and alignment research in the multimodal space? So there are great research done in the NLP space that tackle both instruction following and alignment. Here, the alignment mainly happens with human that when you have in conversation. So for example, Alpaca takes 52K instruction following data, and Vicuna takes 70 conversations that sums up to 700K instruction following data. So they can build similar models to GPT-4 based on the open source Llama. And we can take this inspiration from NLP to build large multimodal models with these two properties. And this is the work that may be covered by Haotian before in the previous webinar called Lava, which is the very first work doing visual instruction tuning with GPT-4. So the main challenge highlighted in the multimodal space is that the self-instruct needs a strong teacher from the LP side, right? But there's no equivalent teacher on the multimodal side. So how can we use language model to create the multimodal instruction following data? That's the problem trying to solve in this visual instruction tuning paper. So instead of directly feeding images in GPT-2, we know that it's not yet available yet. So what they use is a symbolic sequence of representations to represent that image. In their case, they use a caption and boxes for two reasons. One is they find that GPT-4 can understand both, the box coordinates pretty well. And the second is they are very important to represent the image as informative as possible. So from the box coordinate, you can infer like the relative position or the size of the objects pretty well. Yeah, and they take this two types of context and feed into GPT-4 as a representation of the image. And they prompt GPT-4 to generate this instruction following responses. There are three types of instruction following data they considered. One is multi-turn conversations, so that users can chat with the bot, detail the description, so that long responses can be generated from the bot, unlike the previous image captioning, which is pretty short with just less than 20 words. Lastly, there's complex reasoning. This is more of a complementary to a previous reasoning people are looking at that asks very factual questions about the object relationship or interactions in the image. Here, complex reasoning might require you to take external knowledge that may be already embedded in large language models, for example, Llama. And it's more about implication of the image rather than the image content. So the question here shown here is that what challenges do these people face, right? The image is about a SUV in the parking area where the challenge is how these luggages can be packed into the SUV due to the tight space in the car. So the trick is whatever tasks you want the model to perform in the serving stage, we need to create the corresponding instruction following data for the training so that the model can adapt to it. And back to the model architecture, Lava actually follows a very similar model architecture as we presented at the very beginning. So there is a vision encoder there's language model, and there's a projection layer in between that can align the visual features quickly to the language tokens that the language model are very more familiar with. So we also talked about instruction. So the data was for instruction following, right? So the other part is the alignment. How do you make the language model? In many cases now, it's frozen. So people don't have the capacity to actually tune it. How do you align these two very different features so that it can generate reasonable response? So there is one stage of pre-training for feature alignment, where only the projection matrix are updated. So the W show here in the orange part. And this can be done on existing data set, on just noisy image text pair, because it's a pre-training stage. In their case, they use the CC3 million data set, a subset of it, which are further augmented with belief to captions. So make it less noisy, yeah. And the second stage is the fine-tuning end-to-end to own the instruction following data, where the projection matrix and the large language models are updated. And this can serve like visual chat, as there are instruction following data in that. And they also tested on Science QA, which is a multimodal reasoning data set for the science domain. This part, I feel like it largely depends on the large language model knowledge already embedded in their pre-training. And yeah, I'll skip that part for now. So just some visual examples on how good this kind of research large multimodal model can do. So this image is actually from the Multimodal GPT-4 demo. They show this an image of a man ironing some clothes in the back of the taxi, and the Multimodal GPT-4 can capture that, what's unusual about this image. Similarly, Lava can capture it too. So that means we have successfully aligned the visual feature to the large language modeling. It can perform very strong visual reasoning abilities. Another example is, again, a demo image from Multimodal GPT-4. So the chicken nuggets are placed as a word map, and Lava can also capture that. And something surprising out of the author playing with the demo is that they never trained on OCR tasks or data, but then seems like Lava can also have strong OCR capability when it comes to like very a few words on the image. So it shouldn't have seen Lava in the training data ever, because it's a made up word for the model title, but then it can still capture that it's a written Lava. Yeah. And also it understands that it's a abbreviation or something, yeah, which is very surprising. All this reasoning capabilities, we think it's coming from large language model. So it's hidden somewhere there. It's just how can you get the proper data to actually amplify those reasoning capabilities. So there are quite a lot of research along this direction. And this is actually a very nice summarization of all these different research models or data sets along this direction by my colleague Chunyuan. And this only summarizes from March to June. I believe that there are much more models coming out for this 2 months. But yeah, just as a reference, you guys can use this to search for like relative works. And also a great summarization by Chunyuan. So all these works can be split up into like sub areas. So for example, like if you're interested in other domains like video, there's video chat, video llama, DALL-E, working on building instruction following large multimodal models on that. There's also image generation. There are people working on like how to make model taking interleave image text pair data. That's the multimodal in context learning part. And there are also people doing efficient adaptation, just adding LoRa to the model and make the fine-tuning more sample efficient. And there's also people working on evaluation, building comprehensive evaluation benchmarks, looking at recognition, cognition, reasoning abilities of all this surge of the models coming out. Yeah, so again, yeah, I'm not covering all of that, so feel free to just to check it out yourself. One piece that I want to highlight actually is how do we do robust instruction following? So for example, observation by us is all these models are great when you ask the question that the answer is yes. So we have tested, for example, this hot air balloon can be spotted above the tall tree, right? You don't see any hot air balloon here. So the highlight in red is just a non-existent object. And for example, the second one is that is the woman in the blue pants and the pink shirt sitting on the floor. There is no woman wearing blue pants or pink shirts. Surprisingly, this the current open source large multimodal model like MiniGPT-4 or Lava or Instruction Bleep or MMGPT, they tend to answer yes for all these questions posed to them. So one thing we actually just released recently is how to construct more robust instruction following data that in your data, you actually have negative instances. We do this by manipulating the original data and just adding non-existent elements or just changing the attribute of existing element to it so that you can truthfully answer no to some of the questions that you should be answering no. So yeah, that's the part on building large multimodal model with training a large multimodal model with language models. So then here comes the second part, which James have been listening before. So how do we train multimodal experts with a large language model? That the benefit of it, I'll just spit out at the very beginning, you may not need training on that, right? If you are very low on resource, on computational resource, and there are so many APIs or open source models or, for example, code interpreters online, you can just compose an assistant for yourself without any training. Okay, let's get into the second part. So first, let's revisit the evolution of modeling paradigm, especially the deep learning era. We started with, I think there's something wrong with my slides here, but yeah, never mind. We started with training task-specific models on small-scale, well-annotated data. So this results in dedicated models for each task or even each data set, right? And then we enter an era of like, we see a lot of pre-training done on models. So some people would call them foundation model based on the foundation model definition by Stanford. But yeah, they are relatively smaller scale in today's view, although it's trained on large scale noisy data crawled from the web. And then they require task-specific fine-tuning on small-scale, well-annotated data that we use to train the task-specific models as well. And when you serve them to the user, usually a fine-tuning stage is also required. So it depends on your application, right? You might need to fine-tune your model different and have different copies of your model on when to serve them for different applications. So these models, for example, include like BERT or BERT T5 in the NLP side. And on VL side, we have seen like Uniter, Oscar, VMVL, all in this pre-train and fine-tune paradigm. And then nowadays we are entering a new era of generalist modeling. So the pre-training can be done with a lot more data. For example, on the language side, I think it scales up from a couple of billion to a couple of 100 billion tokens. And on the image side, I don't think we have a good way to quantify like how many images are seen by multimodal GPT-4, but I believe like it's quite large. We are already seeing Google are using more than 1 billion images for their training a large model. So this can be very large, and then most of people cannot, most of the institution won't be able to do it. And for downstream adaptation in context few shot learning with a few demonstration examples or even zero shot can do the job. And this is what we call as large language model or multimodal models nowadays. So including like the GPT family, the Palm family, Llama, Flamingo, and so on. And the model scale is also becoming huge, bigger and bigger. I think a rumor on GPT-4 is that it's 200 billion parameters or something like that. And going back to the instruction tuning we just covered, the pipeline of building instruction following models can be still considered as pre-trained and fine-tuned, right? So for example, for Alpaca, we need to build on top of the pre-trained Llama, then fine-tune a smaller scale instruction tuning data. And for VL models like the Lava we just talked about, there's a stage of image text alignment pre-training. It's an additional stage, additional pre-training stage to the language model pre-training already, right? So, and then do a instruction tuning. So it's still a similar like pre-train and fine-tune pipeline. And people are also switching to a new paradigm as they see the strong capability of large language models that can first following user instructions to some extent, and also to quickly understand like few short examples, so it can be applicable to new user scenarios when you give the appropriate prompts for it to learn from. So taking advantage of the large language model, researchers are now exploring a new paradigm that shifts from just standing alone models for solving finite predefined problems. This is what we see in task-specific model and also the early pre-trained models. And now into synergistically training multiple tools or domain experts to solve complicated open problems. Something like the Lava example on understanding visual memes, or taking the advantage of the knowledge of large language models to solve science QA problems. Yeah, they require higher reasoning, and also maybe a composition of different abilities required on the model. So note that this system can be built without any training involved. So just taking a few demonstration examples to teach the large language model to generate proper calling of the right tool, and you can gather all this knowledge to large language model and make it do the reasoning part. So a little breakdown of the total system paradigm is the user will directly interact with the large language model. And the large language model, based on the user intent, it can be a question, it can be something like, please describe this image. It will plan the tool to use, which tools to use, and also in what order. For example, the 1, 2, 3 here. So the large language model will generate a call to the tools. The tools will get executed. They return the result back to the large language model, and combining all this information and also the conversation history, large language model will do the reasoning part to come up with the answer to reply to the user. So this is a very general framework for the multimodal or even any agents now. And just some literature review, there's this type of framework actually started from the NLP side. So they take tools like calendars, calculators, Bing search engines, and then to try to automate stuff like scheduling a meeting or set up an alarm or something like that. But the caveat here is that all these tools are still NLP tools. So they can do the NLP tasks, but they cannot understand image. And on the multimodal side, we're trying to enable the large language model with visual perception ability by connecting it to multimodal tools. This is also a very fast evolving field. And this diagram here just shows the evolution from actually before ChatGPT to 1 month ago from now. So just in the span of, I don't know, like 8 months, there are quite many works already posing this direction. And all this works actually follows the same trend, like how do we leverage multimodal experts as tools for advanced multimodal reasoning and action. So some of the papers here actually go beyond vision, while our focus today will be just vision focused. They do like audio, robotics, video you can consider as a multimodal input as well. And there are some people also looking into how do you help in the animal research side, which is very surprising for me. So this paradigm, I feel like it's applicable to many new applications, and maybe there are more to come. Yeah. Okay. So let me take React, which is our work, as an example to show you how we can build such a system and what new capabilities can be enabled with this system paradigm. So in React, we leverage ChatGPT as the large language model. So the chat will be the user interaction interface, and we can support inputs and outputs in multimodality, for example, text, image, and video. So React designs the system paradigm to compose numerous vision experts with ChatGPT for multimodal reasoning and action. ChatGPT will be the tool allocator, do the planning, so we'll decide which tools to call and in what order will these tools to be called, based on both the input image and the user intent. For example, the question posing here is how many championship ring did the player on the left win in his career, right? So using that user intent, we'll break down the planning and execution in the next few slides. So I think, yeah, it's great. So as ChatGPT only accepts language inputs, to enable the image as inputs, we simply will use the file path as the placeholder to input to ChatGPT. So for ChatGPT, it will just treat it as some like black box string that it doesn't know what inside of it is, but it knows that it's a file path to the image, so it can be used as an argument for API call or the tool calling. Okay, yeah. And first, when it receives the image, it will try to grasp a general understanding about the image. ChatGPT will plans to use image captioning model for overall description of the image, dense captioning model to get a reasonable, more detailed description about the objects in the image, object tagging to get the tags of the object in the image, and the tags will mention faces, and then it further triggers face detection to get a bounding box coordinates of the two faces. And a face detection may not tell the position of the may tell the position of the faces, but may not recognize the identities of these faces. Then the celebrity recognition is called to get the names of these two persons. For each call, as I mentioned before, the output of the tool will be returned, right? And these outputs, although some of them are like numerical values or not exactly text, but we all serialize it as text and give it back to the ChatGPT. So it will make use of this kind of information and to decide whether it needs to call another tool. So for example, the face detection result triggers the celebrity recognition result, right? Celebrity recognition calling. And or it thinks it gathers enough information, then it just summarize the answer and respond to the user. So as a first respond, in our React design, it will just spit out a summarization of what's happening in the image. So the main important information ChatGPT thinks is there's two celebrities, Kobe Bryant and then Paul Pierce. They are both basketball players. So I think these basketball players are from image captioning or dense captioning result. And now if the user asks how many champion rings did the player on the left win in his career, you don't see it in any of the observations. So ChatGPT, but ChatGPT has the bounding box to decide who is on the left, and also the name of the person on the left, right, should be Kobe Bryant. So it takes that information and further invokes Bing search to find the right answer and then give back to the user. I think it should be 5. Yeah, sorry, no animation for this part. Okay, so with all this external multimodal expert, React is enabled with more advanced capabilities for multimodal reasoning and actions. So here is just a brief overview of all the capabilities we show in the paper. There's solving math and text equations in the image. There's understanding visual condition jokes or memes. There's spatial coordinate understanding. So that one is very similar to grounding, but yeah, it hasn't been shown in like models like Lava before. There's visual planning and prediction. So basically take a flow chart or a diagram of how to make a bread. It will speed out the details for you. There's multi-image reasoning that we'll show an example on that later. There's multi-hop document reasoning. So how do you understand like charts, tables, flow chart, or like a floor plan? Those are examples we show in the paper as well. And other stuff like for recognition, we have like open word concept understanding. So this is new as the sense that previously, if you want to recognize a brand, you may need a brand recognition model, product recognition model. You want to recognize celebrity in their celebrity recognition model, right? If you want to classify some like natural food or plants, then you have another classifier for that. Then with this system, as it chains multiple tools, we can do all of that just with one system. And there's also video summarization, event localization, which I'll also show an example later. Yeah, let's get to the example then. So the first one is the multi-image reasoning. Imagine that you are very organized and you take a photo of your receipt every time you make a purchase. So this is the user scenario we imagine when we come up with this example. Although the receipts are actually from the web, it's not from the same person. Yeah, but what we want to show is ML-React can reason over multiple receipts and summarize your spendings for you. Yeah, this should be a video playing. Okay. In the example we are showing here is we upload 4 receipts one at a time. So each time when you upload it, it does all the tool calling part to do a summarization on the receipt image you have already uploaded. So you see like a response under each image. It summarizes the spendings shown on the current receipt image first. And after all 4 receipts are uploaded, we first ask a very simple question with only one receipt involved. So how much did I spend on the grocery shopping, right? This one is only associated with the third receipt, the shop receipt. So first, ML-React can correctly identify that grocery spending should be from the third receipt and return the total amount as the answer. And a second example is like how much did I spend on dining out? It will be only for the last receipt, and also it successfully get the answer. And let's go even harder by asking, how much did I spend on travel? ML-React correctly identifies the flight ticket, and the Uber ride should be categorized as travel and return the summation of the spendings on first 2 receipts. And finally, if we ask how much did we spend on tax, ML-React will getting the amount of tax I paid from all 4 receipts. And note that for the grocery receipt, there's no tax shown in the receipt. So you see like it gets like 3 numbers. Yeah, I think 3, right? 2 numbers. Okay, there's something wrong. Yeah, but I think you guys get the idea. I think there's one receipt also didn't show tax, maybe. Yeah, so this is about like reasoning over multiple images at one time. Yeah. The second scenario I highlight here is multi-round image editing. So this is actually not the main focus. We presented ML-React paper was more on the understanding side, but as a prominent work along this direction was visual ChatGPT, which calls different image generation or editing tools to do like the chat-enabled image generation. So this is also doable. Like it's in the same spirit that you will chain all these tools and make the large language model to plan to what tools to use. The benefit of having an understanding model behind is that you can pinpoint to whatever object you want to manipulate. So the example shown here is that you change one object at a time, right? If you don't have a visual understanding tool behind, then it's pretty hard to narrow down like which part of the image you're gonna edit. Yeah. And finally, for the video analysis, we try a video of Kobe's last amazing 3 minutes in his NBA final game. And the whole video is about 7 minutes long. Okay, so To break down a little what's happening behind is we also take the ASR output from a speech transcription tool, input to the ChatGPT model. Then React will gather both visual and audio, the transcript information to give you a summarization of this video. Once we have the detailed summary of the video, we then ask grounding questions. For example, how did Kobe win the last 2 points to get 60, right? Explain and provide me a short video highlight. So for the first half of the question, it only requires React to explain it verbally, while for the second half, we want to get a temporal grounding output with the exact start and end time when the free throw happens. So what's showing on the right is actually the grounded timestamp. We just cut the video for presentation purposes, and then React can accurately locate the shots where Kobe makes the free throws. Yeah. So there's a lot of ways that you can improve this new paradigm. I'll just go quick. I think I'm almost on time. First is you can extend it pretty easily by switching up large language model or by just adding more tools to it. So we show example in the paper that if you upgrade ChatGPT to the language-only GPT-4, you can see similar effect to the multimodal GPT-4. So this is a very interesting example in multimodal GPT-4 that's solving this. I think it's a foreign language, but I don't know exactly which language it is in. And physics problem, I think. Yeah, so with ChatGPT, the knowledge of the large language model is not there yet. So it cannot answer this question correctly. But with GPT-4 language only, it can spit out the same answer as the multimodal GPT-4. Another example is, I think this may be the future. Will we get replaced by, models? If you just draw a simple demonstration of a website, then multimodal GPT-4 can just quickly write the code and get your website ready, right? So this also, we tried this with ChatGPT. It generates a website, it generates HTML code, but yeah, the caveat here is that the button is actually not working. So it just shows the punchline to you. While with GPT-4, the coding capability is also improved. So you can see that the layout is better and also the buttons are actually working. Yeah, and on adding tool side, there are a lot of work on this thread as well. So one prominent work I want to mention is that if you combine it with a visual foundation model, SAM, that's segment anything, you can mimic human pointing in the conversation as if we use Scribble or Click or just bounding boxes, call the SAM to get the actual region of your scribbles, then it's sort of mimicking human pointing when you are having a conversation with a human. You may point into objects around you, right? So this is a very interesting direction as well. Then you can just add more tools. For example, integrating all the models from Hugging Face, or add even GitHub models or code interpreters. This is what the Chameleon paper is about. So all this adding more tools comes in as the benefit of the plug and play design of the framework. As long as you tell the large language model what the tool is for and how to call the tool, it can just reason over and then leverage that tool. And there's a grand vision in taskmetrics.ai that you can just connect millions of APIs and enable like AI Copilot, AI of Things, office automation. Yeah, it's still a concept yet, but yeah, I think this might be a future. Okay. Due to the time limit, I think I might just skip this part. Feel free to, I think I would share the slides if there's a channel. Yeah, feel free to check it out later yourself. All this part is just on like applications or, how to improve planning of the tool. So there's other things I want to highlight as well. For example, tool creation, right? We have existing tools already, but then if the existing tool cannot solve your problem, can we create tools on the fly? So this is a work on the NLP side that it just creates Python programs to solve like math problems. While before they call like Wolfram Alpha API to do it. It's still a proof of concept, but I think this may also be a future. There's also people working on like how to automate the model training pipeline with ChatGPT. So there's a word called AutoML GPT. If one day we can create new deep learning tools, then you can imagine that this agent can be fully automated. Like you don't even need to tell what tools it can use. When you build a system, it can just create tools itself. Pretty amazing. And also like retrieval-augmented multimodal agents. This is also inspired by the research from the NLP side that we can also think of the document online now as multimodal documents. Before they are looking at like pure text document retrieval to augment the large language model's knowledge, but then with the multimodal agents, can you retrieve multimodal documents to augment the model's knowledge as well? And another scenario may be like if we have a product database with just image and the pricing, then a multimodal agents to retrieve the corresponding price, and when prompt with the product image taken by the user would be also a beneficial user scenario. Yeah, and another direction, I think this is the last one, is on how do we evaluate all these new models coming out, since the existing VO benchmarks clearly have failed to evaluate them. So one direction is how do you evaluate multimodal agents on the multimodal tool using. So API Bank is designing this system like to systematically evaluate whether the model is calling the right tool or not. And on another thread is if we see this emergent capabilities, like for example, multi-image reasoning that no benchmark has covered before, or some example in this picture that if you want to reason about the math equations written by the girls in the image, right? It requires a lot of integration of a lot of core capabilities. For example, recognition, spatial awareness, OCR, and math. Then no such benchmark is actually testing on all these integrated capabilities. So we make the first attempt to build such data set as a first step to evaluate emergent capabilities of all these models. And here is just a result table, maybe too many numbers to look at, but we see that there are cases where the instruction following models are doing better, and there are cases where multimodal agents are doing better. So this leads to my next discussion. Okay, more of a conclusion slides. We've covered two ways to build advanced multimodal system with large language model, right? One is visual instruction tuning. One is training multimodal tools with large language models. There are pros and cons for each side, each of this method. For example, the instruction tuning one, you can build an end-to-end model that directly interprets rich semantics in the multimodal inputs. but it requires data curation and training. So it's more expensive. Now we don't involve human in the loop, but I imagine in the very near future, there's going to be human in the loop building large multimodal models as well. Then the human annotation is also quite expensive. If you don't scale this up, then it might limit its capabilities. So one negative example I haven't shown on Lava is that it doesn't really solve long text OCR. So for example, the physics problem solved by multimodal GPT-4, Lava is not there yet. I mean, it's limited by its perception as well. The visual perception is not really great. And on the other hand, on the multimodal agent thread, we may not need training. We can just use few short demonstrations. And we can leverage abundant off-the-shelf models, APIs, code interpreters as tools. While the cons is no training means we can have failures in tool using. And if we connect the model with weak domain experts, it might give you noisy output that can eventually confuse the large language model and lead to weak performance. So I guess then it's a more research question. Like we now have an open source large multimodal model, for example, Lava. Can we use that as a tool allocator? So it's easier for us to fine tune the model. And if we can use that, then what capabilities would be enabled by a tool, right? Would be required to have a tool to enable, and what scenarios can be solved by just instruction for tuning itself. So these are just very open questions. I think the field might move towards this direction. That's just my personal hunch. Yeah. So a recap slide, finally. We have answered 2 questions on how to build a general purpose multimodal interface. One is training a multimodal with model with a large language model, and the other is training multimodal experts with large language model. So as an acknowledgement that the content of this presentation mostly comes from our tutorial talk. So if you are interested in all the topics we cover in that talk, feel free to check out this website. Yeah. Thank you.
Awesome. Thank you so much for this super in-depth walk through, different research abilities and the progress of the field. For folks who have questions, yeah, feel free to either unmute yourself or I'll put it in the chat. Maybe I can get started with like a quick question about evaluation. So I think you have a slide. I think you talk about like the MMVET code base, right? I think evaluating this multimodal is actually quite challenging because it's combined different modalities, and each modality has a specific evaluation scheme. So maybe can you share a bit more about just the general perspective regarding like evaluating, like a journalist model? What could be like the environmental model for the user?
Yeah, so I think it's a very long-term goal. I feel like in the end, evaluating multimodal agent will just be the success rate of the end task. So now we are still at, I would say like toy-like question answering systems, right? Maybe get some of the spending from the receipts. But imagine like a grand vision in the end, if it actually can automate some tasks performed by human, then you would just evaluate the end task success rate, right? Then that would be more applicable, more towards application and more useful. So, but then at current stage, I feel incorporating the single capabilities captured by existing VO benchmarks and just build a more comprehensive set that requires multiple abilities would be a way to actually measure this new emergent capabilities we have never seen before and never evaluated before.
Mhm.
And I think another challenge is if every output of these models are or like long text format, then how do we actually evaluate on long text output as well? So now the popular approach is actually using large language model to evaluate. So give a score on the output. Yeah, I don't have a concrete answer on that. Hopefully I answer your question.
Yeah. And there was a follow-up question from Jay about like, maybe can you just touch on how hallucination from multimodals and any recent techniques to mitigate such an issue?
So yeah, I think hallucination comes from two parts. One is large language itself, it's already hallucinating. And the other is if your visual perception part is falling short, then it brings errors into the output space, right? So for the second part, we can definitely just improve the visual perception model. So the visual encoder at the bottom that feeds into the large language model. And for the first part, I don't think there's a clear answer on the NLP side as well. Like people are still figuring it out. I think the new startup from Elon Musk, the XAI, they are hoping to solve this. And I hope there's success.
Yeah, I hope so.
Yeah, we're also doing a lot of work in multimodal agents. So actually, we're actually gonna be announcing something really exciting in a couple of weeks' time. So hopefully that can
Nice.
be exciting.
There was another more technical question from Tony, and I'm just reading it out. So he said that the expert capabilities can be either extracted from a large language model like Lava or resulted from an external tool like React. How could we combine the advantage of both approach?
Yeah, I think that's relevant to the discussion page I just showed, right? So, so there are works using instruction tuning to improve tool using accuracy for the agents. So that's something like we can definitely combine the both. So imagine that you have an image already, you have the user question, right? Right now, it's purely based on large language model to plan the tools. So if we build a intent and API calling instruction data, then we can tune all this large multimodal model to do better at tool calling. So that's the idea, yeah, I put into the last few slides. Yeah.
Great, awesome. That's great. I don't see any other question in the chat. So yeah, and also we 5 minutes over time. But yeah, it looks like a lot of people are still sticking around. So clearly it's a very engaging session and
Thank you.
educational.
I feel like I talked too fast.
Yeah, and you didn't even like go over like, all the application slide, right? All those
Yeah.
through. So yeah, I mean, unless there's not any other question, yeah, thanks everyone for showing up, and I asked Lindsey for the slide, and yeah, share the recording, with all attendees, via email as well as our Discord channel. So thanks everyone for showing up today, and yeah, we run this session on a weekly basis, and we'll definitely have more, speakers in the coming weeks, both on research side, but also like sort of more startup and engineering side as well. So hopefully we can see more different perspective from how to implement all this excellent research work that they just presented into the real world. Thanks everyone for showing up, and yeah, hope you enjoy the rest of your weekend.
Yeah, thank you, James, for the invite, and everyone for showing up. Bye.
Thanks, everyone.